Welcome to K11 Tech University. Today, we're going to tackle a question that's so fundamental, most people just take it for granted. Why on earth do computers think in bits? So let's just dive right in. The first thing you have to wrap your head around is this kind of counterintuitive idea. That incredibly smart device you're watching this on, it doesn't actually understand anything the way we do. Not words, not pictures, not even simple ideas. Okay, so if they don't get ideas, what do they get? Well, it all boils down to something incredibly simple, states. And you know what? It turns out they only really need to understand two of them. I mean, think about the simplest possible system, right? A light switch. It can be on or it can be off. That's it. There's no maybe, no kind of on. Or think about the answer to a basic question. It's either yes or it's no. The simple two-state split, what we call binary, is, believe it or not, the fundamental language of every single computer ever built. And this tiny unit of information, this yes or no, has a name, a bit. It's just short for binary digit, a 0 or a 1. But here's the really mind-blowing part. Everything you see on your computer, the words on the screen, the most complex video games, even the most advanced AI, it's all, at the end of the day, just a massive collection of these simple little zeros and ones. But that should make you ask, right, why only two? I mean, wouldn't a computer be way more powerful if it could understand 10 states? Or 100? Why would we ever limit ourselves to just on and off? Well, the answer has nothing to do with elegant math. It's all about physics. You see, the early computer engineers ran into a huge problem. The real world is messy. Electrical voltages go up and down, signals fade out over a distance, and there's always random electrical noise floating around. Trying to build a perfectly reliable machine out of unreliable parts, that is a massive headache. Just imagine for a second, you're trying to build a machine that has to know the difference between 10 different voltage levels. A tiny bit of static, a little power flicker, and bam, it thinks a 6 is a 7. The whole thing would be a house of cards, super fragile. But what if you only had to tell the difference between two broad states? Just high voltage for a 1 and low voltage for a 0. All of a sudden, it's super easy to tell them apart, even with all that noise. The system becomes tough, reliable, and that, right there, is the whole secret. We don't use binary because it's elegant or beautiful. We use it for one super practical reason, because it's reliable. It was the only way they could figure out how to build a machine that would actually work without constantly messing up. All right, so bits are reliable, we get it, but their power goes way deeper than that. You see, a bit isn't really just a number. At its heart, a bit is a decision. No, seriously, think about it. Every single thing a computer does, every complex algorithm, can be broken down into a gigantic chain of tiny, simple questions. Is this thing true or is it false? Do we keep going or do we stop? Do we go left or do we go right? That's all it is. And that is the key to everything. Bits are the simple mechanism that lets computers make trillions, literally trillions, of these tiny decisions every single second. And that's how this mind-boggling complexity emerges from absolute simplicity. You just do it incredibly fast. So, okay, how do we get from a simple yes or no all the way to, everything we see and do on our screens? Well, it's all about building things up, layer by layer. It's kind of like a pyramid. At the very bottom, you've got your bits. You take 8 of those little guys, stick them together, and now you have a byte. Okay, now you can use those bytes to make things like numbers or the letter A. You put those together to get data, you organize that data into complex structures, and then, finally, you write algorithms that tell the computer what to do with all of it. And that's how you get behavior. And listen, this isn't some old school history lesson. We're talking about right now. Even the most advanced AI systems, the ones that feel like pure magic, are still running on physical hardware that, when you get right down to the metal, is just flipping ones and zeros. It's all built on that same foundation of simple binary decisions. Okay, so why have we spent all this time geeking out about this? Why does any of this low-level stuff actually matter to you? I mean, whether you're a developer or just someone who's curious about how this all really works. Well, here's why. If you don't get this fundamental layer, then so much about computers feels like weird, unpredictable magic. You know when a number suddenly flips and becomes negative for no reason? That's overflow. Or those bugs that seem to pop up and then vanish into thin air. Or a system that's just slow and you have no idea why. It all feels random. But the moment you do understand bits, all that magic just vanishes. And what's left is engineering clarity, Suddenly, you see the boundaries. You get the physical limits of what you're working with. You can actually start to anticipate where things might break. You can design safer, more robust systems, all because you know what's really going on underneath. Look, this isn't just trivia for a quiz night. Getting a handle on the real-world constraints of the machine, that's the first big step you take from just being a tool user to becoming a true professional. This, right here, is where engineering maturity really begins. So, where do we go from here? Well, this is just the beginning of our journey down to the foundations of computing. In our next explainer, we're going to build directly on all of this. We'll take a much closer look at what bits and bytes actually represent, and we'll explore the critical reason why their size matters so much. This is where all this intuition starts to become a real practical skill. Here at K11 Tech University, we don't just chase tools. We build understanding. Thanks so much for joining me. I'll see you in the next one.